Good day to you, dear members, and welcome to the solution video of the advanced puzzle Pentagon Pleasure, published April 12th of 2024, and featuring two regular pentagons, so with 5 vertices each, and one of the vertices of the smaller pentagon is exactly the center of the larger pentagon. And also what is drawn is two line segments, one from this vertex of the large pentagon to the top vertex of the small pentagon, and a parallel line segment originating from this vertex of the large pentagon to that side. And this line segment divides this side into two segments with color yellow and green, and the question is, what is the length proportion of these two line segments? And I'm gonna take an approach which makes clever use of the generalized angle bisector theorem. Well, let's come back to that later. But first of all, I'm gonna find some proportions. Because the information that this vertex is the center, that's very, very handy. Let's draw the points. If you look here at this triangle, from here to here to here to there, what you then know, because this is the center and it connects to that vertex, and this line is parallel to the baseline, the common baseline, then it is very easy to see that here we have a right angle. Yeah. Also, what's easy then, and that's very well known in the pentagon, that here we have a 36 degree, let's draw that, a 36 degree angle. That will come in handy later on, but it's not useful now. Okay. So let's put in some length. What for convenience I will call this little line segment GC. Let's say it has length 1. Yeah, because we are looking at proportions, so we can set that 1 to 1. Then the remainder of this small pentagon side, let's say it has length X. Now, from this right triangle, we can, and because here we have an isosceles triangle, we know that basically we have here a semicircle which is centered in G. Or you can also draw the full circle. Yeah, because there is here a right triangle, we know that this is a diagonal, and because of this isosceles, we know that the center is exactly this top vertex of the small pentagon, which does mean that because here we have the length 1, the radius basically 1 plus x, we know that that is also over here, so we have 1 plus x over there. Yeah. Okay, and it's our task to find x. Well, for that we're going to look here. If you look at this small triangle, we know it is a so-called, it's isosceles, because here we have here a 72 degrees, right? Because from the large pentagon we know that this must be 72 degrees. There we had a 36 degrees. Well, it's very easy to find that here we also get 72 degrees. So this is a isosceles triangle, and in fact, because of the 36 degrees, it's the golden triangle. And what we know from the golden triangle, well, here it is isosceles, of course, but we know that the short side is 1 over phi in length of the larger side. So let's put it over here. Phi being the golden ratio. That's why it's a golden triangle. So if this would have length 1, then these would be phi. So therefore their proportion is 1 to phi. Yeah. And finally we know that because here we have a parallelogram, that can easily be seen. We know that this length is also 1 plus x. Yeah, that's the side length of the small pentagon. So we have here another 1 plus x. Okay. So now what we had found is that on the one hand, this is the side length of the large pentagon. So on the one hand, we have found that it has, the large pentagon has length 1 plus x plus x divided by phi. Yeah. Well, let's first give that a place. Okay, it's over here. Yeah. But on the other hand, we have also that same length is over here. So CD is also the side length. So we know that this must be equal to 2 plus x. Yeah? 2 plus x. So here we have found an equation in a linear equation in x, and it's very easy to find that. Therefore, we know that x must be phi. You can easily solve that. X equals to phi. That's the solution of this linear equation. So we have found that this has length phi, this is length 1, and this is length 1 plus phi. Now, why did we go to all this trouble to find those lengths? Well, let's draw 2 line segments. One from here to here and one from here to here within the large pentagon. First of all, this line segment is parallel to this line segment. Yeah, that's inside the large pentagon, and you know that these are parallel. But we already had this parallel line segment given, so therefore we know that the angle between them is the same. Let's say the angle here is alpha. Then that alpha must also be here. Yeah, that's because the 2 lines are parallel. This parallel on this and this parallel to that. But now this line segment is also a diagonal of the large pentagon, and it must be parallel to this line segment of the large pentagon. And again, we have that parallel line segment given, so the angle between those 2 segments is also congruent. So here we have beta, and we have beta over there. Yeah, so now we're going to use the generalized angle bisector theorem, which states that if you want the proportion of those 2, then that can be found by the proportion of the sides times the proportion of the sines of those angles. So what do I mean is that 1 plus phi, remember we have found that x is phi, stands to 1 is the side length, the proportion of the side length, so the diagonal, which is phi. Well, I will clarify that later, times the sine of alpha divided by the sine of beta. Okay, where is it? It's over here. Let's clarify that. So the proportion of this line segment to this line segment is, first of all, the proportion of this side to that side. Now that's very well known within a pentagon. That's phi. So that's this phi times the proportion of the sines of the angles. So sine alpha divided by sine beta. Well, you can easily see that 1 plus phi is equal to phi squared. That's very well known. So on the left side we have phi squared. So you can easily cancel out one of the phi's. So what we found is that the proportion of the angles So sine alpha divided by sine beta is equal to phi. Exactly. Yeah, that comes out of this equation. But now we're going to look at this triangle, and which is divided by the line AF. And now we're going to come at the proportion of yellow to green again, divided by green, equals the proportion of the size, so 1 divided by phi, times, again, sine alpha divided by sine beta. Yeah, let's put it over here. So the proportion which we are finding, so yellow divided by green, is this divided by this. Well, again, we have the 1 to phi proportion times the sine of the ratio of the sines. But we already found that sine alpha divided by sine beta is phi, and lo and behold, this exactly cancels out with this phi over here, so we get that this is 1. And there we have our answer, that the proportion of yellow to green is exactly equal to 1.